Hi, I'm Miss Ramah, and today we're tackling one of the topics GCSE Physics students find trickiest: transformers and the national grid. By the end of this lesson, you'll understand how transformers work, the transformer equation, the difference between step-up and step-down transformers, and exactly why the national grid uses them. Let's get started and dive into the fascinating world of physics. First, the big idea. Imagine pouring water down a pipe to move it a long distance. You could use a thick pipe with lots of water moving slowly, or a thin pipe with less water moving fast. Both carry the same energy, but one is better for transport. You could use a thick pipe with lots of water moving slowly, or a thin pipe with less water moving fast. Both carry the same energy, but one is better for transport. That's exactly what transformers do with electricity. They change the voltage and current, while keeping the power the same. A transformer is made of two coils of wire, a primary coil for the input and a secondary coil for the output, both wrapped around an iron core. Here's something crucial to remember. Transformers only work with alternating current, or AC. They do not work with direct current. And this is the key reason the national grid uses AC. So how do they actually work? When AC flows through the primary coil, it creates a constantly changing magnetic field. That changing field passes through the iron core and into the secondary coil. By electromagnetic induction, the changing magnetic field induces a voltage in the secondary coil. That changing field passes through the iron core and into the secondary coil. By electromagnetic induction, the changing magnetic field induces a voltage in the secondary coil. Energy is transferred from the primary to the secondary, with very little loss. The iron core is used because iron carries magnetic field lines really efficiently. Now there are two types. A step-up transformer has fewer turns on the primary and more on the secondary. This increases the voltage and decreases the current. A step-down transformer is the opposite. More turns on the primary, fewer on the secondary, which decreases voltage and increases current. Step-up transformers are used at power stations, and step-down transformers are used at local substations before electricity reaches your home. Here's the transformer equation. The primary voltage divided by the secondary voltage equals the number of turns on the primary divided by the number of turns on the secondary. In short, the voltage ratio equals the turns ratio. In short, the voltage ratio equals the turns ratio. And because power is conserved in an ideal transformer, primary voltage times primary current equals secondary voltage times secondary current. So if voltage goes up, current must come down. Let's do a worked example. A power station produces electricity at 11,000 volts and 100 amps. It uses a step-up transformer with a turns ratio of 1 to 25. Using the transformer equation, the secondary voltage is 11,000 times 25, which is 275,000 volts. Now using power conservation, 11,000 times 100 equals 275,000 times the secondary current, so the secondary current is 4 amps. Notice the voltage went up 25 times and the current went down 25 times. The power stayed exactly the same, 11 megawatts. Now, why does this matter so much for the national grid? When electricity travels down long cables, energy is wasted as heat in the resistance of the wires. And here's the critical point. Heat loss equals current squared times resistance. So if you can reduce the current, you dramatically reduce the heat lost. Let me show you. Transmitting at 11,000 volts with a current of 1,000 amps, the heat loss is proportional to 1,000 squared, which is 1 million. But step the voltage up so the current is just 40 amps, and the heat loss is proportional to 40 squared, which is just 1,600. That's over 99% less energy wasted, carrying exactly the same power. That's why the grid works in stages. Step-up transformers at the power station raise the voltage for efficient transmission. The electricity travels long distances at very high voltage. Then step-down transformers at substations bring the voltage back down to a safe 230 volts for your home. Then step-down transformers at substations bring the voltage back down to a safe 230 volts for your home. Let's check the exam technique. If you're asked why transformers only work with AC, the answer is: transformers need a changing magnetic field to induce a voltage. AC constantly changes direction, creating a changing field. DC is constant, so the field doesn't change and no voltage is induced. That's a guaranteed mark if you phrase it like that. Now it's your turn. Pause the video and try this. A step-down transformer has 2,000 turns on the primary coil and 40 turns on the secondary. The primary voltage is 23,000 volts. 1. Calculate the secondary voltage. 2. If the power transmitted is 460 kilowatts, what is the primary current? Have a go. Ready? The secondary voltage is 23,000 times 40 divided by 2,000, which gives 460 volts. For the primary current, use power equals voltage times current. 460,000 equals 23,000 times the current. So the primary current is 20 amps, and the secondary current is much larger because as voltage steps down, current must step up to keep the power the same. Well done if you got those. And the secondary current is much larger because as voltage steps down, current must step up to keep the power the same. Well done if you got those. So now you understand how transformers work, the transformer equation, step up versus step down, and why the national grid relies on them to save enormous amounts of energy. I'm Miss Ramah, your personal AI tutor, available anytime at askmissramah.co.uk. Keep practicing, and I'll see you in the next lesson.